bent triangles. My God, what will they invent next? Warp triangles. Okay, for this, we begin with a couple questions that lingered from the other day, which had to do with parallel lines, okay? And some people have problems with that, and it leads to the issue of today. Someone says, if we extend parallel line segments, remember what a segment was? It's chopped off at the edges, okay? Or raised, they will still be parallel, okay? If we extend arcs, which you see there, okay, as you have drawn, we will have circle inside of circles. We come back to the same collinear point. Who gave you the authority? Who gave you permission to extend? Why did you extend my lines? I gave you no permission. I signed no contract to extend any line. More so if it's a line segment, right? So this is the problem. The problem is people extend because they say, well, a line extends forever. Whatever that is. Because if a line extends forever, it's not a geometric figure. And if it's one-dimensional, it's not a figure because no figure is less than 2 dimensions or more than 3. Okay? So what this fellow is talking about is an itinerary. Again, a bunch of locations. That's why he can extend it. Maybe he's talking about the number line, saying there are more numbers. And numbers are just counting, means, again, motion. So all this is motion. So it's got to do with, not with geometric figures, it's got to do with itineraries and movement. And this fellow continues, a line is infinite, again, the infinite line, in 2 one-dimensional directions. One-dimensional. I don't know of any figure that is one-dimensional. So if a line is one-dimensional, it's not a geometric figure. And if it can be extended infinitely, or to infinity, or however you want to say that, then we're not talking about geometric figure either, because all geometric figures, objects, things, are those which have shape. And something that is infinite, it doesn't have shape, okay? Because we're not finished drawing it or imaging it or whatever. You're still sculpting that thing. Okay, so infinite, it means really incessant itinerary or counting. Itineraries have no dimensions, and objects do have dimensions. Okay, so let's distinguish what these people are saying with what geometry is supposed to be founded on, which is figures, things, objects, as we call them. Okay, and another fella comes up there along the same lines. He says, parallel lines are lines angled at the exact same degree. Thus, they never meet. 2 lines with even slightly different degrees will eventually meet on an infinite plane. All these people talk about infinity. They're lost in, I think it's drugging. Maybe they inject too much into their veins. They go always to infinity. The only way they won't is if they both have the same degrees. Well, here I showed the other day a square, which is a plane. It's known as a plane in science, okay? And we have no use for it, but these are just notions that we have. So we have these figures. We call it a square. And when you say square, people think about that black stuff you see there. And I have 2 lines on it. They're 2-dimensional. Okay? These lines are 2-dimensional. You can see they're 2 dimensions, not 1-dimensional. Okay? We have 2 lines. That's what I see in front of it, objectively. That's what I see in front of me, objectively. Square, 2 lines on a square. 2 lines, geometric figures, 2-dimensional each, on a 2-dimensional square, which is what I have objectively in front of me. Okay? They don't represent anything. That's what they are. Okay? Let's get that straight first. Okay, so we have 2 lines on a plane. They're angled at different degrees, and they do not meet. We're done. Are those 2 lines parallel? And so this is what you got to do. You got to do with what is objectively in front of you. And so this notion about extending lines to infinity and planes to infinity, well, we can't use that because, see, there is no plane that is infinite. No square that I know of that is infinite. No circle that I know of that is infinite. No triangle that is infinite. And for sure, no line that is infinite. All lines stop there. You draw them, wherever you draw them, that's where it ends. You got to analyze whatever's in front of you, objectively. And these people, have little birdies in their head. They say, well, what if we take it to infinity? Well, I've never been there, so I don't know. It's like saying, what if we extended to heaven? I don't know. I've never been there either. And I hope to forestall being there. Okay, so what was my summary the other day? Let's start with that. Essentially, summary for geometry, okay? Geometry is not a branch of science. Not what we have today. Not what Euclid did. That's not part of science. Geometry is a branch of religion. Geometry is a branch of religion. Okay, we got that straight? Why? Because it's an attempt to merge mathematics with physics. That's why. And that's impossible. It's irrational to try to merge math with physics, physics with math. Math has to do with counting numbers and all subsequent developments from there. And physics has to do with objects, with mechanisms. One has nothing to do with the other. You can do all the measurements you want. In math, you can calculate, you can do equations, you can do derivatives and integrals, algebra, whatever. I mean, I've done a lot of math, and I was good at it. I like math a lot. But it has nothing to do with physics. Physics is about mechanism. Tell me how the window broke. I don't need to know how much mass, how much energy, how much force. I need to know what broke it. Okay, and you can say, well, like Felix did there, he threw a brick through it. Okay, that's how the window broke. That's my theory. The window broke because I threw a brick through it. We're done. That's physics. It's got nothing to do with math, which is, let me calculate the speed, the mass, all that stuff. One thing has nothing to do with the other. Okay? And when we talk about Mother Nature's universe, we're talking about physics, right? We're talking about how she does things. We want to know, we want to understand how she does gravity, how she does electricity, how she does magnetism. Not measure and say, well, this is how fast she did it, or this is the acceleration of gravity, or what the force was, on the charge, or anything of that nature. We don't care about that. That's math. We want to know we understand the mechanism, how Mother Nature's doing these magic tricks. Imagine a magician in front of the audience on the stage saying, doing his trick, and you say, well, can you explain that? Oh yeah, here, he did it at so much speed. He cut the lady in 2 pieces. He did it at 10 strokes per second. I don't care about it. I want to know how he did the trick. That's the difference between physics and math. We don't need numbers in physics at all. Okay? We're talking about 2 different things. One is a language, which is math. The other one is a science. Okay? And so geometers misconceived all fundamental figures. They misconceived the point, the line, the plane, the circle, the square, and the triangle, as we saw the other day. Okay? Geometry has to do with measurement. Okay? Math, not with figures, which is what physics is about. Okay? The part we care about geometry are the figures. Okay? Not how they behave, or what their ratios are, or what their relations are. Okay, so let's get on to the triangle, especially the bent triangle, the warp triangle, which is the subject matter today. And we start with Euclid's definition of how he came up with the triangle itself. What is a triangle? We have to first identify the word triangle. Well, this is where we have a problem already. Okay, he begins with surface is that which has length and breadth, meaning, again, it's not breadth, it's known as height and width, not even length or breadth. Breadth is a vector, not a dimension, but whoever, either Euclid or his translator, never figured that out. Okay, the edges of a surface are lines. Okay, no, the edges of a surface are known as edges, okay, not as lines. Okay, plane surface is a surface which lies evenly with the straight lines on itself. So he's going to make his surfaces, his planes, okay, he's going to make them with straight lines. No, because according to him, lines are discrete entities. And if they're discrete entities, space separates any 2 lines. I don't care how many gazillions of lines you put in between 2 lines, there's still going to be space in between there, because otherwise you can't talk about lines. Okay? So he started off on the wrong foot already. But he says a boundary is that which is an extremity of anything. Okay? And a figure is that which is contained by any boundary or boundaries. Perfect. The only problem is he never used that definition, and no one has. Well, that's the first problem. The second problem, more fundamental, is no one discovered that that's the foundation of physics. That's how important that definition was. So no one ever discovered that, how important it is, and no one ever used it. So irrelevant anyway. So there it is, staring at you in the face, definition number 14, one of the foundations of physics. No one saw it, no one understood it, no one figured that it's important. That's where the problem is. So that's where we start, and then he goes on to define what a triangle is. He says rectilinear figures are those which are contained by straight lines, okay, which is not true, but trilateral figures being those contained by 3. And then he continues on with other rectilinear figures. And he just goes into definition 20 and 21 into different types of triangles. So what is a triangle? Well, it's a 3-sided thing, figure, whatever you want to call it. Okay, so we started off there, but did we improve on that? Well, no, we only got it worse because we got all these wrong. Here we have the circle we talked about the other day. It's just an orbit of a location, not even of a point, because the point is a location. Here we have the square. Okay. And what is a square? Well, a square is a path around a perimeter. Again, it's just a bunch of locations That's all that it means to a geometer, a mathematician, not a physicist. And here we have the triangle. The triangle is not even that. The triangle, you don't even need three sides. Today they define it as just 3 points. If you have 3 points, you have a triangle. So that's a triangle, according to them. I don't know, that doesn't look like a triangle to me. It looks like 3 points. 3 disconnected points, that's what they look like to me. But this is what they say is a triangle. So this is where we already start on the wrong foot. If that's a triangle, well, yeah, I can see how they got lost over time, okay? And important here, Euclid essentially said that his triangles, the plane triangle, 3 angles, right, amount to 180 degrees. And here it is, okay? This is just one example. He wrote a lot of propositions and etc., okay? And he tried to prove them, what they call mathematical proofs, okay? And proposition number 9, just an example here, okay? To bisect a given rectilinear angle. And what he does is he chops a triangle in half and he just figures out that they're rectilinear angles, so both of them meaning 90 degrees, and the 2 sides essentially of that triangle equal 180 degrees. So through this proposition and others, you can look at the whole series, especially in book 1, and you'll find out that essentially he's talking about 180 degrees. Okay? It's all related to 180 degrees. We're done, right? Now, it was too boring. It was too boring, and so they had to change that, and that change started in the early, you could say the first half of the 19th century, okay? And it started with this fellow. His name is Nikolai Lobachevsky. Okay, and he one day he took his triangle, which he put on a piece of paper, I guess, right? And by mistake, he happened to put it on the saddle of his horse. And when he did that, he found out, hey, it no longer has 180 degrees. It's got something different than 180 degrees. Well, another fellow came around a few years later, again, 19th century still. His name was Bernhard Riemann. And Riemann, instead, he put it on a soccer ball, I guess, right? And he said, hold it, this piece of paper, which I had it flat on my table, now I put it on my soccer ball, and the angles seem to have grown bigger. Of course, neither Riemann nor Lobachevsky realized that, they were encroaching on the 3rd dimension. See, if you take a square and you twist it around, like, now you don't have it on the same plane, you don't have just width and height, but now you twisted it in such a way that you also give it some depth, in other words, meaning you gave it the 3rd dimension, which in this case is length. Well, now you have length, width, and height. So that square is now in 3 dimensions, and just because you tilted it, assuming, you could have a square in the middle of space, right? God can do that. And if you twist it around, it's no longer a square. Now it becomes a rectangle. And you can do that with almost any figure. If you turn a circle around, right, if you could get a circle, a 2-dimensional circle, right, and you have width and height, and you turn it around such that, from the viewer's point of view, it now occupies a 3rd dimension, well, you no longer have a circle, now you have an oval. It changes its shape. And so the question is, are you allowed to do that? Well, this is what these folks did. They put their triangles into the 3rd dimension. They bent it into the 3rd dimension. Okay, and it's like, oh ho, yeah, we did it. Okay, so now we have a difference. And what did these gentlemen conclude, Lobachevsky and Riemann? Well, this is what they concluded, essentially, okay, in a nutshell. They said, look, when I put it on my horseback, I get less than 180 degrees. And the other guy said, well, you're wrong. See, when I put it on my football, soccer ball, whatever, baseball, basketball, I get more than 180 degrees, especially if it's malleable, right? Unfortunately, they don't make triangles which are not malleable. And so when they do that, it says, I get more than 180 degrees. And they started messing around with triangles which are not triangles, not in the old-fashioned way. And again, triangle means 3 angles, right? And they say, well, so if you got more than 180 degrees here and you got less than 180 degrees there, and they said, yeah, see, the way they calculate those angles now is they take the tangents. They take 2 of the tangents and they calculate that separation between the tangents. Like, if you put a tangent there on the ball, on the triangle, the Riemann triangle that's on the ball, you just take any point. It doesn't matter. Along that curve, and just take 2 points, put a tangent there, and that's how you calculate the angle at that point. Okay, so that's how they do it in general terms. Okay, so that gives you an idea how the math developed from this notion that these folks had. So you say, well, Bill, what's the problem with that? I mean, geometry, it's measurement, it's calculations, it's angles, it's sine, cosine, you know, all that kind of stuff. Trigonometry, you know, that's good stuff. What's wrong with that? What's wrong with giving it a new notion to the triangle and to these lines? Well, I'll tell you one of the problems. There's a couple of problems, but I'll give you one other problem. One of them, they ended up with curved dimensions, okay? And here you have an idea of what these people did, okay? See, Euclid had these straight dimensions, length, width, and height. We're done. Simple. Everybody understood it. These folks came up with the curved dimensions, essentially. You know, you have curved width, curved length, and curved height. And that complicated things a little bit because, you know, now we have a different language. They put a new language starting in the 19th century, which is, you know, these curved lines, because they have to account for how they reshaped the triangle. Okay? And you say, well, still, what's the problem with that? And here's the problem. Here's the problem, one big problem, okay? And it's known as the geodesic. Okay? Geodesic is a curved dimension. It's a curved, a curved dimension, essentially. Remember the circle? Well, they say a circle has no insides. It's got no guts. Circle is just a circumference. It's not this. It's not a disc. People criticize me and say, "Oh, Bill, but yours is a disc. It's not a circle." Well, we call it a circle because the disc or the circle, one of those two words is too much, is irrelevant. Because if the circle is just the circumference, we call it circumference. If the circle is the disc, we call it a disc. Then why do we need the word circle for this? So they say, well, the circle is that what you see there, just the outside, the perimeter. And remember, it's a bunch of dots, okay, because and those dots represent locations, meaning that what you're staring at is just a bunch of locations. You're staring at an orbit. And so now the question is, okay, so we have this circle. Let's even assume, if you want, that's contoured by a solid line, continuous line. Okay, so far so good. Now I want to get from A to B. Very simple, right? Well, I want to take the shortest path. The shortest path is a straight line. We call it a rectilinear itinerary, not a straight line, because we're not talking about lines, geometric lines. We're talking about itineraries, which is another issue. Okay, but I take the shortcut across, you know, the red one there. And they say, you can't. You got to take the one on the outside. And I say, why? That's longer. No, it's the shortest path. What do you mean the shortest path? The shortest path is the red line, the red dotted line. And they say, well, see, not on a curved surface. Well, but you don't need to do that with a circle because a circle has no guts. It's got nothing in it. It's empty on the inside of the circumference. Why can't you take a shortcut? And they extrapolate this notion to things like the Earth, like, you know, a sphere. Perfect sphere, again, is empty on the inside. It's a solid that is hollow. A hollow solid. Okay, that's what a sphere is. So if a sphere is a hollow solid, why can't I cut across the inside? If there's nothing there to stop me, why do I have to go through the surface? Well, that's when they say, well, you can't do it on the Earth. That's why you need a geodesic, because on the Earth, you have the shortest path is not through the Earth, you know, like going to the center of the Earth. No, you got to go around the surface. So that's how the geodesic was introduced. And now you can see also the idea of bent triangles lying like on the Earth on a solid, which is not hollow. Okay, this is where we're getting to this. And we ended up with something like this. If I can get it here. Part of it is language. Let me cover that real quick first. Okay, and just like, you know, you don't do rectilinear, you don't do straight lines, you do rectilinear itineraries. And you say, well, that's semantics, that's just wording. Well, see, they have all this rotten wording everywhere. You know, spin is not spin, particle is not particle, okay, in mathematical physics. And then we have situations like this one where you have NASA and they say, and I just took a snapshot of this by Googling it, you know, in the image region, okay? It says, NASA, how gravity warps light. Another one by astronomy.com. Bent light if photons have no mass, blah, 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 blah. Okay. NASA, how gravity warps light. Okay. And another one, gravity must bend light. So we have warped and bent light. And is that what we're saying? We're warping a photon? We're bending a photon? We're taking a little photon, just bending it in half, warping it? Is that what these people are saying? No, they're using the wrong language. What they're saying, it's been deflected. They're saying that a series of photons, in fact, they draw it, a whole bunch of photons, right, little particles that supposedly represent a ray of light, and it curves around, it is warped around, right, because it's not really warped or bent. What you're having is it's being deflected supposedly by the warpage of space-time, which is alleged to be a physical object. You have this warped time, and the little photon is sliding along warped time, and it's not being bent or warped. That's space-time that's warped or bent. What the little photon is doing is it's being deflected. Okay, so language is important. And again, we have that same problem when they confuse rectilinear with straight, or curvilinear with curved. You know, curved, you can say that a hammock or a banana is curved. But when you're talking about itineraries, now you're talking about something else. You're talking about rectilinear. It's something moving rectilinearly or curvilinearly. Okay? You're talking about how it moves, you're not talking about its structure. And so the language is important, especially when you're talking about geometry, which is about figures. But since these people don't talk about figures, they just talk about itineraries, which they represent with figures, okay? And you're not supposed to take the figure literally. Well, that's where they get confused. Instead of talking about the motion, they say straight. No, you don't move straight, except in ordinary speech. In science, you have to say rectilinearly. Okay, that's how motion is. Okay, and so now, yeah, you can see how how these bent triangles and geodesics create big problems. Because here you have two elephants, okay, and they're moving along geodesics. In other words, they're moving along curved path, the shortest path. And it turns out that they say that this is what causes them to be attracted to each other. This is the mechanism of gravity, the mechanism of attraction. They say that because they move along geodesics, that's the cause, the mechanism of attraction. So you can see how dangerous all this stuff is, because that's not an explanation. You can't say that that's the mechanism that brought these two elephants together. That's a description that says that if they moved along these two curved surfaces on a sphere, they get closer together. That's a description. That's not a cause. That's not a mechanism. You see how dangerous the language is and why geometry, having been misconceived from the start, ends up with these kinds of conclusions. Okay, so yes, it is important. It's more than language. It's conceptual. Okay, we've lost track of what we're talking about because these people are introducing motion in the guise of objects. They represent them with objects, then they can get confused between the object that represents the motion, and then they use the wrong language because they're describing the object, not understanding that they're actually describing motion. And you don't use adjectives to describe motion, you use adverbs to describe motion, to qualify motion. This is where it gets so dangerous because people get lost in what they're really talking about. So when they talk about particle, you think of particle. Yeah, I know what a particle is. A particle is like a speck of dust, a grain of sand. And so they talk about the motion of the particle and they give a 2-hour dissertation. And then you say, well, was that really a particle? And they say, well, you're not supposed to take the analogy literally. No, it wasn't a particle. It was the collapse of the wave function that was moving. They're talking about a number. They're talking about an equation. They're talking about a function. And they're talking about the location, how you can locate the particle, the so-called particle, the location, how they can locate the location in a certain location. That's what they're talking about. And so, yeah, after a while, you get dizzy. You don't understand at all what they're talking about. They don't either. They think they gave a physical interpretation.